Hello?
Yeah.
Is it working?
Yeah.
Yes.
Okay. So, this week for those guys. Today's Friday noon speaker is Danny Theriot from Quebec City. And I learned to know him when I did my PhD postdoc at Université Laval. And he was a physicist and working with radiosurgery. And now he's moved on to Levy Clinic, and he's starting up a whole new center. So Danny did his undergraduate and master's at Université Laval, and he did it in nuclear physics. For his postdoc, he switched over to medical physics, and he might speak about that during this talk. Maybe.
Yeah, maybe.
So, welcome. Stage is yours. Does he need to use the mic?
No, there's one on the podium.
Okay, thank you for the introduction, and thank you very much for the invitation. I'm very honored to be here. When I was looking at all the list of the nice talk that were given here, I was kind of impressed, basically. I know that probably a lot of the talk were more on the academic sides, but me, obviously, I'm a clinical medical physicist. So my primary job is really to basically to open a new center and make sure that the clinic is running. But as Shirin was saying, also I have a background in kind of more fundamental research stuff, and it's still stick with me. And I'm trying to get some ideas, and some research program also alive in that setup in the new building we're going to open. And so I'm going to talk a little bit about how we can use like the uniqueness of Levy and what's in their hyperbaric facility and other stuff to know where we're going with that and what kind of research we want to do basically about that. And I'm going also to discuss a little bit of development we're doing regarding failure mode and effect analysis, which is based on the TG100 that you might know for safety in radiotherapy and risk analysis in radiotherapy. So we're doing some work also on that because obviously that's a big part of the clinic. And yeah, so as Shirin was saying, I came from nuclear physics. I remember when I did the switch from nuclear physics, I was studying the equation of state of nuclear matter for neutrons and protons, and that had some sort of utility eventually for astrophysics. And I was very proud when I switched to medical physics because I could finally explain my family what I was doing. And, at the first Christmas party, I was there with my family uncle, and I said, you know what, I'm working at the hospital. And they were looking at me, oh, great. And they were staring at me like, okay, you're finally, starting to give back something to society a little bit. So I know a little bit the prejudice also about fundamental research that sometimes you can face, but okay. So I'm a little bit of both. Okay, so the main focus of the presentation would be the CRIC, which is Centre Régional Intégré de Cancérologie en Chaudière-Appalaches, which we're building it right now in Lévis. So it's just beside Quebec City on the South Shore. So just to give you a rough idea, it's pretty much like the same size of the Charlemagne expansion that was done about that. So it's basically a new building that is in construction. There about 14,000 square meter. So it's on 3 floors. The first thing you'll notice in the name, you'll notice that I didn't have time to translate all my slides, so you have to figure out my international conference, bad English, or you try to learn some French. Okay. So the word cancerology really refers to cancer. So it's really a project. It's not only a radiotherapy project, and that's something that is very important. When I got there in 2014, there was already a philosophy behind that project that I fought for, even as a medical physicist, that involved a lot of people and a lot of general organization of clinical care in cancer. So everything, the philosophy of that project is that we need to have as the most people involved with cancer at the same place, working together to get a good treatment and to be efficient for the patient. That's basically the clinical goal. So everything's going to be in there, and we're all working together. So that means that physically there's going to be like one staff room, for everyone. So you're going to have lunch with the social or nutrition worker one day, and you still share with people in chemo and physics. So I got to meet those people also and know them, and so sometimes it can be a little bit difficult to understand each other, but we're doing that. So it's also an integrated center, which so integrated is a little bit of a buzzword in management. It's used a lot for a lot of stuff. But what it basically means, the bottom line is that it means that you have to have the service organized in a coherent way, basically, for the patient. And what does it, in a very concrete way, what does that really mean for the patient is that, of course, you have to have a building where you can put all the service at the same place, which is kind of obvious. But you cannot right now you cannot examine a patient in the cloud or something with computers. So you have to have a building. But it's also very important that all those professionals in that building work on the same basis, and we're a paperless center. So it's very important, the IT part and the communication part, which is really the backbone of the structure of the center, that work efficiently. So for us, it was in the project, that's something we also fought for a lot, is to have a unique oncology information system that will be implemented in all the structures. So that's very important. So just a quick technical description of the center. So we're going to open next year in April for radiotherapy, but the center is going to open in January for general consultation. We'll have 4 linacs starting the center, but I think we'll go to 5 somewhere between 2020 to 25. But according to the number I just saw, I think it's going to be closer to 19 than 25. So there's 6 bunkers, so there's a swing bunker. We have 2 bunkers also that where the excavation is a little bit deeper, and we also have a removable wall to pass eventually MRI or MRI linacs, which is so that the project is already compatible with this kind of technology that in 15 years down the road we could have in radiotherapy. So the path is already planned for that. I even put some quench pipe across the concrete, make sure that in the future we don't have to drill there, and I shield them. And so we're really planning ahead. When you're building a center like that, you're basically building for the next 50 years at least. And so you don't know exactly what's going to happen, but you have to be robust enough and flexible enough so that you can accommodate most of the technology. Planning CT, planning MRI on site, which is something that is great. I think I'll talk about that a little bit later. And in the project also, there's a PET CT that is still in nuclear medicine. It's an expansion of nuclear medicine, but it's basically really a radiation therapy simulation room. So it's full with laser and table and all that stuff. Quickly, on the chemo side, it's 21 chemo unit, but I'll go quickly about that. And we also have dentists and all the other service needed for cancer treatment. So that's the PET CT. So the PET CT is here. So that's Hotel Jude Levy, and that's the new building we're building at the back. So that's the expansion that is already open. So the PET CT is a biograph. We commissioned it, and it's working right now. So it's a very nice machine. And as I was saying, you can see the laser, and we'll have flat table, flat couch top table, and everything. So it's really a radiotherapy simulation room where we could do, for instance, the lung patient, basically. So I'll go quickly also with the architectural design. So that's the building. It's on 3 floors. So what we call the second basement is really the technical radiotherapy basement. So you have the bunker with direct door to save some space, as I was discussing with William. And you see the 2 bunkers where we have those opening there. So that's the radiotherapy. At the center, you see there's this space that is empty. So that's going to be a healing garden for the patient that we kept natural with flowers and trees. You have the planification on the left side, which with the MRI, CT, and everything for the patient to be for the planification. Of course, physics. We'll try to get a sign like here for medical physics. It's pretty cool. And brachy is also a big thing. You can see that it's fully equipped for anesthesia and full procedure basically. And we have 2 good doctors in brachy, so I think we'll be very employed in brachy, and we can go to the MRI pretty quickly with a path this way. So it's so that's the technical basement, and then you have the more the first basement is more staff, people who get the office and some meeting room and that kind of stuff, and the employee rest area, which is common. Like I was saying, everyone's going to be at the same place. And you have on the ground floor, that's where the patient will be coming in, and then you have all the consultation rooms, chemo, and the welcoming places also. Just a quick staff update, because I used to be alone with a couple of people in that project when I was in 2014. But then I would say like right now, almost every month we get new people in there. So I will just pop up a couple of slides. I cannot present everyone. There's a lot of people involved. So our medical team right now is led by Dr. Daniel, which is presently working in Quebec. And we have Dr. from CHUM, Sophie Lavertu, Mélanie Gianet, who comes from Rimouski. David is a resident in CHUM right now, and we have our 2 brachy doctors. They're always together. Dr. Laurie Pilote and Émilie Bouillard. So Dr. Laurie Pilote just came from a fellow with Dr. Crook in BC. Émilie, I think, is going to go to UCSF, and I think she's in some sort of freestyle brachy with no template and this kind of stuff. I'm not a brachy guy, so I don't know what that exactly means, but that's what she's going to be working on. And the therapists also are all in place, so all the coordinator. We have people from everywhere, basically. And we have Michel Sanson, which is our system pilot. That's an important job that sometimes is kind of ignored or put on the side a little bit. But that's someone that is taking care of the oncology system full time to make sure that the scripting, the workflow, and everything will be in place for the paperless clinic and efficient. So that's very important to keep the system alive and in phase with what the clinic needs. So that's very important. So he's working full time on that job. And of course, the physicist, so Mathieu is coming from Quebec, Danny from CHUM, Jonathan from Rimouski, Nadia also from Quebec, and Jean-François is still in residency, but he's been working at CHUM also. And I have a job slide a little bit later, but we have a job opening right now, and we'll be hiring also 2 other physicists next year, so I'll show that a little bit later. Quick slide also about the equipment. Then I think I'll move on to some research and perspective that we have. So we're going to be having Electa machine. So it's 4 Versa HD full equipped when we open. So everything that's in there, we have it. So it's so all the modes. We're going to be using the Hexapod table. So we're still trying to find out and figuring out, in which case we're going to use it versus not. So the oncology system that I was just talking about is Mosaic, basically. So we're investing a lot of work in mapping the workflow and scripting everything. It's already done almost for all the chemo part, and the chemo part is going to go live with Mosaic before we go in the center this fall. So we want to go in step, and there's a lot of work to do in there. So it's not easy. So we have a blank page, as I was saying this morning, in front of us, but we want to make sure that we start on the right foot and try to not develop bad habits right away. So that's so there's a lot of pressure to commission that system, and we have all stuff of goodies in there with Mosaic to scripting and the documents, and so we're working on that. So the CT, so it's pretty much a standard CT. The MRI is something that I'm kind of proud of, because I think we were the first center to be really involved in those large tender process where usually radiology is buying the MRI in that setting, but we were able to actually build a process in which the radiation therapy equipment was evaluated specifically for our needs for radiation therapy. So that means basically that we went on visit to evaluate really the coils and to make sure that we were able to set the patient for planning without deforming their anatomy, and that the dockable table were working fine for brachy, because we have 2 dockable tables. One will probably go in brachy to treat on the MRI table directly. And so it was a nice process. So Siemens won the thing in the end. So it's a 1.5 Tesla with a lot of equipment in there also. And of course we have the flat couch top and laser. So it's going to be a full radiation therapy planning machine. And CT on rail for brachy. So in the brachy suite we have this CT. Elekta won also a process for brachy, so it's going to be the Flexitron system. We have all kind of applicator and the new Venezia and that stuff the doctor liked a lot, so we'll be working with this system. The dosimetry, we're going to be basically a RayStation center, so the main dosimetry system is RaySearch. And so just to scan a little bit the things we're working on right now with the system is MCO, multi-criteria optimization. So we're trying to figure out what role is going to be to play in the clinic exactly. Automated breast planning. We have also module for that we bought for dose tracking. So that allows to accumulate the dose on CBCT and take the clinical calls to know when we want to replan or not. Just keeping, yeah. And so that's very interesting. Deformable registration that goes pretty much straight with the dose tracking also. Adaptive planning, which allows to take into account doses that were already given to a patient when you're replanning, and to do it in a coherent manner. So that's very interesting. Biology, not so much for the biological optimization itself, because it's based on NTCP and that kind of stuff, and we could discuss that a long time. But I think it would be useful in the clinics for the tools that it provides for biology, radiobiology calculation if you stop a treatment, and fractionation and that kind of stuff. So that's something that's going to help us. And virtual simulation if you just want to treat a patient fast in APPA, a good old school fashion. We also are going to have CRAD for surface imaging. So we had a lot of discussion of where we will be going with 4D and all that kind of stuff. And I think CRAD is and surface imaging in general with Visionary. So it does a little bit the same thing as Visionary. If you know the system, the physical principle behind it is a bit different, but it's pretty much doing the same thing. The nice thing with this kind of system is of course you can do the 4D, you can do the application like the IBH and gating, but you can do a lot of other stuff like checking the positioning of the patient and having like this kind of color settings for the color projection on the patient for the therapist to know if the position is okay, that kind of stuff. And CRAD is also working on a translation, checking also fine-tuning of translation for head and this kind of stuff that could be used for if you need more precision for certain treatment. So that's a system that is offering a lot of possibility, I think, in the future. We also have we're going to use also EPID in vivo dosimetry. Once again, that's something we are evaluating right now, how much we're going to do that and what place is going to take in the clinic exactly. But basically, it's a project from Elekta that they just developed from the approach in Netherlands, where their back projection. So Netherlands have been working a lot on back projecting the measurement of the EPID in the patient, and Elekta just packaged it in some sort of nice software that looked this way. So that's something we're going to use also in the clinic. Aqua is going to be the system for all everything that is machine QA and all QA basically. So it's going to be the management system for all the QA. So the nice thing with Aqua is that it has a sort of XML interface that allows to translate and to make your own test. So it's pretty flexible, and it's vendor neutral, for what it means. But you can plug with different equipment also. So it's very nice. So we're very proud of that. And we're going to be using Delta 4 also for IMRTQ, which is basically a diode array, 3D array on 2 plane. The nice thing, since I'm at McGill, we're going to be using DevDocs as a document management system. And so we've been working, so thanks to John Kildare and his group for helping us install the system. And we start working on that to translate the interface. And we start, on building some of the protocol we're going to use in clinic. So we're actually working on that. We still kept the name DevDocs as a tribute to the original DevDocs, but we're working a little bit on that. And same thing for sales. It's pretty much the same thing. I think it's a very good system that was developed here, so we're planning on using it for clinical application also. Okay, so I think I'm doing good on time. I'll talk a little bit about some development and research that we're also doing or planning on doing at Lévis. Like I was saying, of course, we don't have like a big academic structure, but I'm trying to get some momentum to promote some research in Lévis as the chief medical physicist. So there's one unique thing that is not, I think, very well known in the community, is that at Lévis has a pretty big, in fact, hyperbaric facility there, a hyperbaric medicine facility. In fact, I think it's the biggest in Canada and one of the biggest in North America. And I think there's some historic reason for that. But when I got there, I found out that there was this very nice infrastructure, and I remember when I was in radiosurgery, a lot of paper, especially in Japan, where they were testing hyperbaric pretreatment for sensitivation of tumor with radiation. So I talked with the doctor there. I talked with our chief radiation oncologist, and we're trying to get something going on research-wise with this facility. So what is basically hyperbaric medicine? So hyperbaric medicine means that, so that's the facility right now in Lévis. So it's pretty big. So that's the main chamber. But there's also a research chamber, actually, that we could use for research purposes. So and also going with all the hyperbaric chamber, there's all the staff that goes with it that is trained, and we have a specialized the doctors that are certified. So there's a special certification that in the U.S. for hyperbaric medicine. So we have this kind of very unique, I think, things going on in Lévis. And so what is basically hyperbaric medicine? So hyperbaric medicine basically is any medical procedure that you do under an environment where you have a pressure that is higher than the regular atmospheric pressure. So it's the analogy with diving is that when you're diving, basically the pressure increases. And those people, they're talking in diving terminology. When you go there, they say, okay, we have a dive at 1 p.m. and this thing. So you feel like you're in Florida and Key Largo. It's minus 20 outside. You go there and say, okay, we have a dive at 1. Okay. And so they're really talking with this terminology. And so everything that would happen in those chambers that will require to have a higher pressure than the regular pressure, atmospheric pressure, is considered hyperbaric medicine, basically. And one of the main applications, of course, of hyperbaric medicine is that usually you would put the patient in there and you make them breathe oxygen with this higher pressure. And what does it do? Basically, this is what we call the HBOT, which is hyperbaric oxygen therapy. So what does it do, in a nutshell, very fast, is that it increases a lot when you breathe oxygen at the regular atmospheric pressure. Most of the oxygen is in the red blood cells, basically, and is carried by those cells. What it does, the hyperbaric treatment, is that it increases a lot the level of oxygen that you can dilute in the plasma of the blood. So it changed a lot the configuration of the oxygen flowing in the patient. And there's also some tricky vasoconstriction effect and all that kind of effect that we've been discussing with the doctors, hyperbaric doctors. But what it does basically is that it increases a lot the oxygen in the plasma. So that's pretty much it. And right now, if you look at HBOT, there's some established clinical application for that. So so that's pretty much the list of the Undersea and Hyperbaric Medical Society, cool name. And you see, of course, among that list that there's an application that is recognized right now for radiation-induced injury. So unfortunately, as you probably know, sometimes there's necrosis and this kind of complication that can arise from radiation therapy. And by using that treatment and increasing the oxygen in the wound itself or the necrosis, it can prevent necrosis, or it can stop the propagation of tissue that are necrosing. So that's one of the applications that is established regarding radiation therapy. And there's already been some clinical research going on with the facility in Lévis to treat those treatments, to treat those patients. Sorry. So that's a project that was conducted in collaboration with the Université Laval by a resident, in which he was following bladder inflammation problems for patients that had previously radiation therapy. And so what basically the slide is saying is that the HBOT is promoting angiogenesis, and when you're breathing oxygen under the kind of patient the pressure that would be 2 times the atmospheric pressure, you increase by 10 the level of oxygen that flows in the blood. So that's a very big effect. And basically our result is that for that kind of side effect, the patient are able to maintain 71% of the patient are able to maintain a good efficiency regarding that condition for a long-term healing of that problem. There was also some research going on with the LOEX, which is a tissue lab, tissue generation lab in Quebec, and the Université Laval and the medical physics group regarding also tissue wounding induced by radiation therapy. So basically what happened is that there were some mouse that were put under a big bolus, and we induce an injury. I was talking with and I said, poor mouse. I mean, so there were very high dose of radiation that were given there. And there's many arms to that study, and it's still going on. But what they saw basically is that when we were putting the mouse in they had a small hyperbaric chamber for animals. And they saw, an improvement in the wounding and the closing of the wounding with that kind of treatment. So on this, I would say that, and of course the dose was measured with a nice plastic scintillator that was put in the mouse. So the plastic scintillator was adapted for in vivo measurement with the mouse, and a pretty high dose of radiation were given to the mouse. So I would say that this is kind of more established application for hyperbaric treatment regarding radiation therapy, which is basically to try to improve the condition of patients that had previously radiation-induced problem. But the other kind of application that is far less well established is to use HBOT, prior to radiation therapy, to try to use it as a radio sensitizing agent, basically. So that's something that is far well established. There was some I will show a couple of slides about it. There was some research about that, but this is something that in Lévis I think we could eventually test on a clinical situation, setting. So where does that ID come from? Basically, it comes from the fact that we know that oxygen is very important in radiation therapy. When we're working with radiation therapy with photons, basically at the energy we're working usually in clinic, most of the damage are produced by indirect reaction with the environment. And we know that it comes from a lot of chemical reaction that would eventually, with the OH radical, damage the DNA basically. But the thing is that to ultimately fix the damage, you need ambient oxygen. Otherwise, there's always chance that the damage basically in the DNA will be repaired. So that's basically the oxygen effect. That's where it comes from. So you need oxygen to fix the damage in the DNA. And the other thing we know in solid tumor basically is that you can have hypoxia, because basically when you're in normal tissue, the angiogenesis naturally will make the tissue well perfused, and you have enough oxygen for the tissue to grow normally. But you could also, because in tumor the angiogenesis is much more chaotic, you can have region where you have basically you have low level of oxygen. That's something that is known also, and you could also conceptually after that separate that lack of oxygen with diffusion hypoxia or perfusion, which is basically the distance. You could call that diffusion limited hypoxia if you're far away from vascularity, because the cells closer to the vessel will consume the oxygen. And you could also, if you have this kind of effect which is clogging, you could call that perfusion limited hypoxia. But basically, there's hypoxia. That's what it means. And we know that hypoxia is an important prognostic factor. So in general, I remember when, going to a conference where I saw the first slides about really this kind of effect in my life, and I realized that we're not talking about some sort of one person control whatever after 20 years on a tumor. It's a kind of very important effect, and if you compare, and you can do it in many ways, but there's some clinical paper that really shows that a patient, especially for head and neck and GYN tumor, that has hypoxia, we're not doing a very good job. And I think it's an important factor that will prevent the tumor to be controlled because of the lack of oxygen in a part of the tumor. So that's a very important prognostic factor. It's also the case, that's an older paper, but as I was saying, for GYN cancer also. So once you know that, then you have to figure out if you're able to first identify hypoxia, and that's where imaging comes into play, and that's very important. And there's different techniques to try to assess hypoxia in a tumor. There's a lot of stuff that you can use. I would say that the one that are the most available to clinics right now would be PET-CT and MRI techniques. The disadvantage of PET-CT is that you have.
Attention, code search Glenn Adult.
So the disadvantage of PET-CT is that you have to use markers that are giving a lot of radiation basically to the patient, and it's not very user-friendly if you're going to use it many times during treatment and to assess how hypoxia is reacting in the treatment. So I think MRI techniques are interesting to assess hypoxia eventually. And also in MRI, there's different way of doing that. You can measure perfusion, which is not directly hypoxia, with technique like dynamic contrast enhancements, where you process basically a set of image to a pharmacokinetic model, or you can use both techniques that are used in functional imaging and this kind of stuff. But there's also a nice project here, I think, that is led by Dr. Levesque and Véronique Fortier that I saw, that is trying to measure hypoxia basically directly with susceptibility and chemical properties of oxygen directly, which I think is a very interesting idea. So MRI is a good candidate with some of those sequences to assess hypoxia. So the idea right now in Levy is that we have this unique setting where hyperbaric oxygen facility and technique is there. We have we have a facility where we have radiation therapy almost at the same place, and we have MRI and PET CT in radiation therapy right away. So what we're trying to do right now is to get money and grant, and we did some application to start some research program regarding those things. So I think Levy is going to be in this unique setting where we can maybe develop a program to test hyperbaric medicine in radiation therapy. And that's the other. That's a couple of clinical trials that are going on or that have been going on regarding this kind of technique. There's one in 2016 that was published where I think it's about 20 patients in the U.S. that were for head and neck cancer that were treated with hyperbaric medicine before radiation therapy. So since it's a phase 1, so it's really to prove that it's something that was well tolerated by the patient, but it doesn't have any statistical power, obviously, to prove that it was efficient, but still it proves that it can be done. So that's interesting. Okay, so that was for hyperbaric medicine. The other thing I wanted to talk about today that we are working on right now in the CRIC regarding development is about mapping the risk in our clinic. So when you're opening a center like that, you can do anything. So that's nice, but then you have to figure out how you're going to make the clinic safe. And as you probably know, it's a complex problem, and sometimes you end up as a medical physicist as taking a decision regarding the QAs and that kind of stuff in meetings where people are saying, oh, I read that paper and I think we should do that, and so we had those discussions going on, and so we tried to make a reflection about that, so right now we're working on a model where we will be mapping the workflow, the total workflow of the center. I will explain a little bit how it's working, basically. And I don't know if I don't have a lot of time, but I will show a couple of slides. So you probably heard about TG100, which is, I have to say, a paradigm shift at least once. So let's say it's a paradigm shift. I don't know, but. So it's a different way of seeing basically QA in the clinics. So task group 100, basically the couple of facts that are brought up in this paper, in this task group, is that, of course, the complexity in clinics is always increasing, and it's not going to get better, I think, because you have different systems. It can be a nightmare if you have a big clinic and different system, and you have to transfer information, all kinds of parameters. So what do you do with that? Because you have limited resource, and also the fact that was brought up in this paper, which I think is very interesting, is that most of the big errors that happen in radiation therapy, the worst I think that were publicized in the last year, were human being errors. So it doesn't have to do with a leaf that was wrong or a parameter in a machine that was like half a millimeter, off. Of course, you have to follow that, but it doesn't kill a patient basically right away. So the worst error that passed through the radiation therapy process in the last year were linked to process. So what the TG100 brought up is that maybe we should start working with engineering, what is known in engineering process as FMEA, so failure mode and effect analysis, which is an analysis basically in which you map your whole process chain, and you try to basically attribute to each step of the process some sort of risk, basically. Okay, I'll talk about that a little bit more in detail. I'll just pop up a couple of slides that we presented last fall. My colleague Mathieu Goulet is working on that also, and he presented a couple of results that at OccupyMC last fall. So, like I was saying, if you in brief, TG100, what it does is that you map everything, And then each process ends up having like an occurrence, a failure mode, okay? So you map all the failure mode, everything that can go wrong in your clinic according to a process. You put to that failure mode an occurrence probability. You put to that failure mode a severity, which means is it dangerous or not. And you put a detectability factor also, which means is it going to get to the patient, or there's a good chance somehow that someone will be aware of that and it's not going to happen. So, and then you map those processes via a fault tree analysis, which is basically, it looks like a tree in which all the processes are drawn, basically. So the problem, there's three main problems that we identify with TG100. So TG100 is a big paper, and it's a big TG group. But at some point, when you read the paper, it kind of finished a little bit brutally, and probably someone in the committee said after 7 years, it was very long. You have to come out with something, and so there's something missing, we thought, in TG100. But it's still a good basis to start the reflection. And one of the main problems is that the failure mode are only for one process, and you cannot accumulate the failure mode. So in principle, you will have many failure modes that will bring to something wrong in your clinic, but the formalism that is developed in TG100 doesn't deal with that. So that's the first problem. The first problem is that TG100 is telling you to, okay, put quality control in there if it's dangerous, but we all know it from a medical physics standpoint that all QC are not equal, and the problem is that there's no way in that formalism to say, will that QC really be efficient in my clinic or not, and is it enough to make sure that I sleep well at night and everything is going to be okay? So that formalism doesn't do anything about that. And the other process is that you can. The other problem is that you can get crazy by just drawing all those fault trees. It's very time consuming, because if you change something somewhere, you have to draw it, and you have to discuss it again, which is. And the other comments I will make here is that if you're planning on going into this kind of analysis, make sure that you start with the right scale. And the right scale, what I mean is that if you go too fine in your process chain, then you become crazy and you will lose your time. And if you go too coarse, the problem is that it's going to be useless, because you're not going to be triggering anything on the process that are very dangerous. So it's kind of tricky. And but the problem is that it's very time consuming. So what we did, the first thing we did is that we wrote a new matrix to express the risk. The problem with the TG100 is that when you look at the scale, you have those ranking there. But when you look at the scale, basically what you see is that you want to give more importance to what is very dangerous or what will happen in the more with more frequency. But the way the maths are done in TG100 is that it just takes what is called the RPM, and it's just the multiplication of the three factor. But when you end up to summing that as a risk, it doesn't propagate in a coherent manner to make it exponential, still exponential. So we just did an hypothesis that it will work better if we use a new matrix that will be exponential. So the risk is now exponential, so that's what we decided to do. And the other thing so the risk, so that's how we propagate the risk in our model. And so that's basically, it looks a little bit complicated, but it's just a sum of exponential, basically. So we're now able to sum some failure mode to know exactly what will be the risk for the total process, which was not the case in TG100. And we couldn't put that also to the square, but I'll just keep that. And we found a way also to evaluate the efficiency of a QC that we can insert in there by using a negative index, basically, ODS index. So we express the QC as a negative index, and we rank them according to our experience. So there's nothing magic there. It's really the experience of the medical physicist that knows if everything will be if something is going to be efficient or not. For instance, you can call us like cynical maybe, but if you just educate people, we thought that it would be almost a 50% efficiency, you know. So if you're just telling someone in the clinic, don't do that once in a time, maybe it won't work that much, basically, okay? So that's how we deal with it from the math side. And so right now we have a way to propagate and to make the QC working in the system. And we developed a code, basically, that is a Python code that is writing XML files that are read by draw.io that makes maps, basically, that are able to draw the whole mapping of the workflow. If you change something, it will just generate that. So it's very efficient, so you don't have to mess up with drawing and that kind of stuff. And you can visualize your workflow pretty quickly. And right now, we're even working with a database that is in which you have all the failure mode, basically. So we're also putting that in order to be more efficient. So, and we did some testing and examples. So that's a concrete testing we did with a question that always arises for a medical physicist in clinic. So should I do like pre-treatment QA for all my RMAT case? Should I use EPID to try to check what's going on in vivo? And, you know, so that's the kind of question we try to answer. And so the process that so that's just a part of the whole tree, but that's just to make an example of how all those trees look. And so the process here will be beam production, which is to produce the beam on the patient. And we have all the root cause here that I didn't really talk about, but that's how it looks a little bit. And so that was the part of the tree without any QC. And if we put QC, which we would call EPID in vivo, and also other QC there, you can see that the risk, the number there should be, of course, should be lower. But it also allows us to see that there's still some processes that we judge that are still dangerous in our clinics, and we might want to put other QCs at the same place. And so we're able to map everything that will be going on in the clinic that way. And we did the same thing with another scenario, which would be to using, instead of in vivo, we compare with pre-treatment QC. And we see that the process, we judge it to be a little bit more dangerous, in fact, because the beam, basically, the reason behind that is that you're not checking on every fraction like in vivo would be doing certain parameters. So that's the kind of stuff we're doing right now. So with this project, but I don't have much time to go deeper. Yeah, we could discuss that also. Okay, so I think I have to conclude. Okay.
Finished?
Not yet. I have a couple of slides. So I thought you were just like coming to tell me that I should. Okay, I'll go quickly. So the milestone just means that the next year is going to be a very busy one for us. So that's pretty much the milestone. It just means that we're going to be very busy. So that's my side about hiring. So we have a job that will be that is post right now. It's for someone that will be in function at the end of summer or fall. But also, I would suggest that if physicists wants to work for the job that will be available next year, they can also submit their CV, because they will be known, and I think it's a good thing. And we might end up, if someone is very good, we might end up also doing some deal to hire them or to pre-hire them for next year. So that's yeah. So that's some view that I wanted to show about the project. And so that's and a couple of construction site pictures. So that's actually in the bunker wall, because when direct door, I had to check that all the pipes that we pass through the concrete before we pour the concrete in the center were at the right spacing to make sure that there was no diffusion and that they were according to plan. So we're not a clé en main or a turnkey project. So the team is really involved a lot in the conception and in the construction also. So that's a little bit like the center looks like right now. So that's the bistro, that's the restaurant we're going to have in the center. And stairs, and that's the healing garden that will be there that I was talking about. Melanie, my colleague, that is the project manager. So that's another view from this winter. So that's the guy I was working with them for the bi-parting door. So we'll be installing a bi-parting door for shielding, and it's it's another interesting topic because NCRP 151 is not really adapt to that kind of situation. So I didn't have any nice Monte Carlo simulation to help me. So I did some of interface and manual calculation about that. For that situation, and that's so that's how it looks. The bunker, and so that's the brachy room, and that's the main bunker places we're building right now. So thank you. Do you have comments?
For this interesting speech, and I'm a very proud friend of you and Matthew for this great center. And I'm also very happy that you got Elekta, Research, and Delta 4, all of them Swedish.
Yeah, I see Swedish. Yeah, that's what I was about to say.
When I was in Quebec City, me and Danny, we used to have coffee, 10 o'clock coffee, because when I came from Sweden, I wanted to have 10 o'clock coffee. And Danny had 10 o'clock coffee with me every day, and I discussed a lot about common coffee rooms. And I'm also very happy to common coffee room there, and also your healing garden. It's almost like being in Sweden.
Yeah. But actually, I think the architects were very influenced by this very minimalist architecture thing of Sweden and Scandinavian style.
And also, I'm very proud of you guys because you see your work inspires people, Veronique and Eve, and also John. So whatever you do inspires people and actually improve the healthcare. So you must just see this as your project and see people are reading your work and they are getting inspired. So I'm very proud of my colleagues as well. And also, when I was a PhD student, I had a consulting firm called Symmetrics, and I did the grandmother simulations of the grandmother of your Delta 4. So that was built on my work, which is also making me very proud. So I went for taking a check or publish activity. So thank you so much. Any questions?
Do you have comments?
Yes. So now you can go. Yes. So Maria?
Hi. I have a very practical question about FDA. You've worked in the clinic before. You kind of know how the workflow goes. After you've done some FTA, is there anything that maybe you didn't see before that you see now as an
Yes,
factory?
that's a very good.
Can you give me an example?
Yeah, we notice that's a very good question, and yes, that's a very good question. For example, when we were doing the work that I did present about the IMRT general process, we realized that at some point we realized that if we will be using only a PID or of a rotating detector, we will not test exactly the correlation in 3D space between the leads that we were delivering with and the position and the actual patient. And so that's that influence, and we didn't really notice that before we did the whole process, that there was maybe a point where that would be missing, and if we would just be using a PID. Because at some point we were maybe planning on using a PID, but the problem is that, a PID, the bottom line is that it's a 2D projection that is rotating basically with your gantry. So so it's okay. It's a test that is valid. But we wanted and we realized that we needed places in the whole process where we would be able to assess that the leads were at the right place with the gantry position. And if you have a detector that was just rotating with the whole thing, there was no way to know that. So that's a very concrete example of something that we notice because we took time to map the system and reflect, take time to think about that, basically.
And what's the process that you're going to have in place? You're going to have Delta 4 for IMR TQA prior to fraction 1.
That's a good question.
You're going to be doing in vivo dosimetry.
That's the good question. And as the chief medical physicist, what I didn't talk about is that the bottom line in the end is that you have to evaluate how much physics time it's going to cost for each scenario, and you have limited times and resources for the staff. And so the decision has to be also driven at some point by management and resource consideration. Right now, we're kind of leaning toward a scenario, to answer more non-politically your question. We're more leaning toward a scenario where we could, in principle, use in vivo dosimetry for a lot of in vivo. I don't think it's very sensitive to a lot of stuff, but we could use it as a check for very gross and direct error with the LINAC. We would do some pre-treatment QA Delta 4. Delta 4 is going to be used for, don't worry, Sharon. Delta 4 is going to be used for the commissioning of the whole center, but it's going to be, I think, in the end, less used for pre-treatment QA. And we'll try to be more intelligent and smart about the way we do the pre-treatment QA. And what we realize also, to answer your other question, is that the pre-treatment QA in the end, if you're doing a good job at the LINAC, is really checking, is really useful for to check your TPS, to check the TPS commissioning, and to be able to identify some situation that you didn't test when you did the commissioning, despite all you do in commissioning. Clinical situation where your TPS might not be exactly right, or you have TPS problems. So what we're leaning towards right now is try to have a second TPS check, and if we see a difference between both clinical TPS, we'll go to Delta 4 with pre-treatment QA, but we'll not always go to pre-treatment QA because it's too time consuming, and we will do that in conjunction with some EPID in vivo dosimetry that will check a lot of gross error that if you just do a pre-treatment QA, you might end up testing once at a certain machine that is not necessarily the machine you're going to treat the patient on. So it's still valuable to do that, but it has some limitation.